Hello everyone, welcome to the live stream. So today we are going to do some ray marching, and before we start doing ray marching, I'll be introducing a platform that I have created. It's a basic WebGL implementation, nothing too fancy. So it's called ShaderPlayground, and it allows you to run fragment shaders in real time um, on your web browser, so you can experiment with different shaders on your web browsers. So I initially uploaded it on my GitHub pages, but currently due to some issue it is down, so I'm running it on my local system itself. I'll soon be resolving the issue and getting it up and running on GitHub pages, so you all can also try your hands on ShaderPlayground. So I'll be using this platform that I've created, ShaderPlayground, for implementing Raymarching, and I'll be explaining what is Raymarching, and like as I code it. So let's go to the whiteboard. Yeah. So Raymarching is a rendering technique. So like graphics APIs like OpenGL and DirectX, don't mind the handwriting here. So OpenGL and DirectX, these graphics APIs generally use a rasterizer for rendering their graphics. And there is also one technique called ray tracing. And ray tracing is like really, you know, confused with ray marching, but these are two completely different yet similar uh, rendering techniques, I would say. So let's talk about ray tracing first before we come to our main topic. I'll write short form as RT, which stands for ray tracing. So it's nothing but we create a virtual camera like so, and let's say this is your screen, and it is divided into different pixels. Don't mind the drawing here, it's just for illustration purposes, and I am using my mouse for drawing, so it's not that good, but yeah. So let's say we have these many pixels on a screen. So what we do, and let's say we have some objects in a scene. Let's say we have a sphere here and a few other objects. Let's say we have a cube as well. And now what we do is we use a camera to project some rays. We shoot rays uh, like per pixel. So like this pixel will have a ray passing through it, and it will go in the direction towards the objects, and so on for each of the pixel. And what we basically do is we shoot these rays from our virtual camera, and we check for intersections with this geometry here. So let's say we are considering this ray right here, and this ray intersects with this sphere at this point. So basically we get this distance right here, and we get this point by adding, let's say this point here is called RO, and this is at distance d where we intersected with a sphere. So basically we do RO plus d in order to get this point, which is RD, I would say, and it is equal to RO plus d. And after getting this point, then we can get the gradient of this point to get the normal of that point, and we can implement our lighting algorithms to light our scene, and basically this pixel corresponding to that ray would be colored accordingly. And what ray tracing does is it uses intersection tests for checking if it intersects with an object or not. And it basically any object, let's say behind this sphere, it won't be rendered because the ray is blocked by this object itself. So this is ray tracing. Now moving to ray marching, our topic for today. So ray marching is a bit different. What you do is you basically we have the same setup. Let's say we have a camera right here, and we similarly, like ray tracing, we pass a ray through each pixel like so, and we have our scene objects here. Let's say this is some object A, and we shoot multiple rays per pixel through uh, our virtual camera. But in this case, what we do is we take small incremental steps. Let me explain. So let's say we have an object A right here. I'll make a simplistic diagram here just for illustration purposes, so it is much clearer. Um, so let's say we have a ray which is going in this direction, and let's say we have an object here which is a circle, and another object, let's say a square, and a triangle right here. We'll name this as A, B, and C, and this is our ray origin. We'll call it as RO, and we shoot this is basically the lens of the camera, you could say. And what we do is we basically use sign distance function, also known as SDFs. So this is nothing but this function actually encodes the geometry into distances. So it is basically, yeah, a encoding function, you could say, in a vague manner. And what we do is, let's say our point is at RO, then we compute the distances of this point RO from each of these uh, geometries. But mind it, in ray marching we are not using any vertices. We are directly using maths to draw render our graphics. So it's more like the vector graphics software that you use, like the Illustrator, Adobe Illustrator. Like all the graphics that you design, it's made using splines and all mathematical curves, and like it allows you to zoom infinitely, and it doesn't tear up like when you zoom too much into the image, because it is defined using mathematical equations, and scaling doesn't have any effect on it. So similarly, we calculate distance for each of these, and let's say at this instant we got the distance from A as let me write it, distance from A as dA, which is, let's say, 0.4. Distance from B, let's say we have it as 0.6. uh, it is just an example, so the distances might not be to scale. And let's say if the distance from our object C is 0.9. So what we do is this sign distance function basically gives us the distance of this point from the boundary, or boundary of this object. So these distances are calculated starting from this boundary of this object. Now we find the minimum distance out of these three. So right now the minimum distance here is 0.4. So our point can march along this ray at a distance of 0.4 without, just getting, mushing into an object. So let's say this, from this point the distance was 0.4. So basically what we do is, I'll draw a circle like so. So basically we can move 0.4, move or march. That is why this method is called, a rendering method is called as ray marching. So we march along the ray with a distance of 0.4, and this allows us to get closer and closer to the object that we will hit eventually, which is going to be our object C. Now again our point is moved to this second location right here, and now at this point again we will calculate the distances using sine distance function. uh, right now just treat the sine distance function as a black box. I'll explain it in details later on. So at this point I again calculate the distances. Let's say from A the distance now is 0.2. From B the distance is, let's say, 0.1, and from C the distance is, let's say, 0.5, like so. So now the minimum out of these is 0.1, which is the distance from the boundary of our circle B. So we can move in the direction of the ray, we can march along the direction of the ray with a distance of 0.1. Let me reduce the brush size. Yeah, and this will basically be another circle centered around our previous position, and it will be like so. And similarly we will march along this ray, and like unlike ray tracing we are not caring about the exact intersection location. Here what we are doing is we are trying to get to a point where the distance is you know around less than epsilon. Let's say d is less than epsilon, where epsilon is really small, close to 0, and at that point we detect a collision basically. And after detecting the collision we get the total distance, and then we like obviously get the point where it intersects. So it is an approximation of ray tracing, you could say. We are not doing exact intersection tests with geometry. And otherwise there might be a case, let's say a ray is going in this direction and it is not hitting any of these objects, and let's say this ray will go it will travel an infinitely long distance. So it won't be feasible for us to keep computing distances with these, because the ray is already escaping right here, it is traveling infinitely large distance. So basically to limit this we limit this by keeping a certain number of iterations. Beyond this we will not consider it as a hit. So that would act as our field of view basically. So this was the concept of ray marching, and we'll be using this for rendering. And let's come to sine distance function. So sine distance function is nothing but it is a function which gives you distance from the boundary of a surface or any object. So let's say we have an object here like so. I'll call it A, and let's say its boundary is known as delta A, and we have a point P right here. So if we write a function distance P comma Q, so we'll get a set basically. We'll use a minimum function and write it in a set builder format. This distance such that this point Q, it belongs to A, which is our surface right here. So I'll write it as distance D such that point Q belongs to A. So this distance D right here is nothing but the distance between this point Q and this point P. The minimum function right here ensures that we get the point on the boundary, because let's say we have a point here, like Q belongs to A, right? So a point can be here, 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 but the minimum distance would always be at a direction which is perpendicular, and the point will lie on the boundary of this surface. But this same point P can lie inside of this surface as well. Right here, we are just using plane distance and not a sign distance. So in this case, we are not making much of the sense, but uh, there is one concept. So let's say at this point P, we have a distance of k, like from this point Q or the boundary of our surface A. Then we get this contour like this, basically a concentric shell that we would call around our original surface, but it is at a constant distance of k from the boundary of our surface A, and this is known as a level set. Level set or a iso surface. So basically, we can get infinitely many such level sets at a distance k, where k will range from minus infinity to plus infinity. It will also lie inside of it. So this is a normal positive distance functions, but let's create a piecewise function which we will call as SDF. So I'll denote it with just D. D of P is nothing but the distance function of P and delta A, where P is outside. So basically, when the point is lying outside the surface of our surface A, then the distance will be positive, and it will be negative when the point lies inside the surface. Delta is the boundary basically, and P is inside. I hope I am audible. Yeah. So this is our sign distance function. So let's say we will use this figure right here. I'll just copy it to a different location. Right here is fine. So let's say we are shooting this ray right here. So let's say we have this ray shot from the camera right here, and at this point the distance from this surface, which is k, is less than epsilon. So we will consider it as a hit, because we are not trying to calculate the exact intersection like in ray tracing. In Raymarching, we are just approximating the hit of the ray. So we stop here, and what we do is basically, now we have this point P, which is at a distance k less than epsilon on this level set of the surface. Now we can get this distance d right here, and using this we will get this point exactly. So basically we are getting this point on the surface, and basically what we can do is we can apply a check that if this point is positive, or basically our SDF is positive, then we will paint this fragment or that particular pixel, and if it is not, then we will not paint it. So basically whenever we hit that object at a surface, we will get a positive value, right? Because it will be at a certain distance, uh, less than epsilon, but it will always be a positive value. So this ensures that we always hit a surface. Otherwise we do not hit a surface, so we'll get negative value, and in that case we can decide not to paint the fragment. So this was a basic explanation of what SDFs and Raymarching is, and let's go back to the platform that I created, ShaderPlayground, and we can try implementing something with the concept that I have explained. So let's create a variable named UV which will store our UV coordinates. I'll assign it to ST, that was basically normalized earlier. And what I will do is I'll transform the space so that the origin lies in the center of our canvas, and basically it will range from -1 to 1 in along x and y axes. So I'll multiply it by 2 and subtract 1 from this. So basically this canvas ranges from 0 to 1 right now, and when I multiply it by 2, so let me show it to you on whiteboard. This ranges from 0 to 1. I multiply it with 2, and we get a range of 0 to 2. Then we subtract 1 and we get a range of -1 to 1. So this is what we are doing here. And now what we will do is we will take the x coordinate of UV, and we will multiply it with our aspect ratio so that things don't get stretched, because the like basically in the clip space everything is defined in a square, and that square is mapped to the rectangle on our screen. So basically it gets stretched, so we need to take into account that stretching, and we multiply it with our aspect ratio. Right now what you see on this canvas is the UV coordinates. So basically this is 0 0, so this is black, and as we move along this linearly, you can see colors being interpolated, and different colors for different values right here. And this is x equals to 1, that means the R value is 1 and GB are set to 0. So this is red in maximum, this is green, and this yellow is actually the mixing of these two. So we have done that. Now let's create a SDF function for sphere. So let's start by rendering a basic sphere. So let's derive the SDF for a sphere first. Let me draw a circle. Assume this is a sphere right here. Let's say this is the center of our sphere and it's of radius r. And let's say now that we have a point P right here, and we need to find SDF is nothing but the distance from the boundary. So what we will do is we will use our distance formula, which basically is derived from the Pythagoras theorem, and find the distance between these 2 points. Let's call this as x. We have this distance x here, and what we will do is we'll subtract the radius of our sphere from this, and we will get this distance d, which is nothing but our SDF. So SDF is basically it, you know, consists of all concentric spheres, ranging from radius 0 to infinity, and it stores all of that information in a single SDF function. It's that powerful. So let's write that. So we'll create a method which will return a float. We will call it SD sphere. It will take vector 3 for the pixel coordinate in 3 dimensions, and we will pass a radius which will be a float, and it will return length. Length is a function in GLSL which basically uses that distance formula, and right here we will be finding distance with respect to origin, so our sphere would be centered at origin. So I'll pass in P right here, and we will subtract R from this, like we did in our derivation back there. That is done. Let's create a function named map. So it will basically, help us map different SDFs together. Like we can combine different SDFs together in order to make complex geometry. And so I'll create a map function where we can combine multiple SDFs and use it together. So map will just right now we have created a SDF for a sphere, so right now it will just return SD sphere. Let's pass in P directly, and let's keep the radius as 1 for now. And now to the main part of this function. Let's create a Raymarching function. I'll name it March, and it will take in RO, which is the origin of our ray, which is actually the camera lens, and RD, which is the direction of our ray. And what I will do is I'll create a variable of type float. I'll name it T and initialize it with value 0. So T is nothing but basically the distance that you travel. We will accumulate the distance as we take march along our ray and take small steps like we discussed on the whiteboard before. And I'll create a for loop. Let's keep it for 100 iterations. So basically, like we discussed here, so if this ray actually gets past this, so we don't want it to travel infinitely, and we don't want to check distances with each of this object infinitely. So we will limit this ray by limiting the number of iterations that we have. So we have set it to 100 iterations right now, so we'll be using that. And what we will do is we will calculate the point here, let's call it P, by using the formula RO plus T times RD. It is nothing but, let me explain. RO here is the starting point, and this is the ray direction RD. So this is the direction vector, and along this RD we will travel a distance of T. So we are multiplying RD with T. We are scaling the direction vector RD with T, and we are adding it to point RO in order to get this point P right here, like so. And what we'll do is we will get the distance, we will calculate the distance. I'll create a variable for that. I'll name it D, and we will use a map function which is internally calculating the SDF for getting the distance from the boundary. I'll pass in P right here, and after doing that, what I will do is I'll do a check. Let's say if D is less than epsilon, so I'll let epsilon be 0.001. So if it is really close to our surface, then we will return our t. Otherwise, we will just keep marching along our ray. I'll just keep adding the distance d from the surface, which will be the smallest distance. And if t is greater than 100, which is our number of iterations, we'll be limiting the distance to which the ray can travel. Then we will break out of this loop and we will return -1. -1 means no collision. So as I mentioned earlier, like uh, it will, you know, it will always return a positive distance. So if it is negative, then we will not render any fragment there. So our Raymarching function is ready. Now what I'll do is I'll create a variable named t again in our main function. I'll use the function march. Also, let's define RO and RD here. So our camera position would be, let's say it is, placed along the Z axis, let's say 3 units, and the ray direction is crucial here. So as in ray marching, the direction would be along the minus Z axis, and for each pixel we'll shoot a ray. So we will pass in UV as is for the X and Y coordinates, and for the Z coordinate we will just add a -1 there, and we will pass these these coordinates to our march function, which will perform ray marching. After that, we will check if t is greater than 0. If it is positive, then we will get a point P, again using the same formula. So right here, we get the point P, and now let's do one thing. After getting this point P, we can, let's say, use a fragment color of white. For now, we will apply a shading model as well to it. And if the distance is negative, that means our ray does not hit any object, we will color it black, just for now. We have an error. Let's check. Frag color. Okay, yeah, it's a variable we have to. Let's remove this at the end, and it should work. Right now you can see this is a sphere rendered using our SDF using ray marching, but it looks flat like a circle. It does not look really good because we don't have any lighting model in place. So let's implement that as well. You know what? In the background we can add a gradient so that we'll get a skybox kind of effect. So let's declare, let's say C1. I'll declare it as a dark color, maybe 0.3 for the blue value, and C2 again a vec3, 0.2, 0.2 and 0.3, 4 maybe. And let's create another variable named color, which will mix these two based on the Y value. Right here, for mixing these two, we will use ST, not UV, because these are two different coordinate spaces. So ST's origin lies at the left bottom corner of our canvas, and for UV the origin lies at the center of our canvas. So we will mix those two based on our y value, and we will pass in the color like so. Let's make it a bit brighter at the top. Yeah, this looks good. And now we will implement a basic Phong lighting model, but lighting cannot be done without getting the normals. So what we will do is try to calculate the normal vectors for each fragment. I'll just have a sip of water. Yeah, so we will basically, let's say we have this SDF. This is our surface and the SDF is like so. So now if we have a point P right here and we want to find a normal to this point, so basically if we imagine it in 3D, it will be something like this and we have contours like this, right? So along this contour or along this concentric shell, our gradient would be 0 because it is not changing anything. But the gradient will always be maximum at the in the direction of steepest ascent or descent, whatever you call it, like so. And this will help us get the normal vector for our fragment. But for gradient, we will basically just normalize our gradient like so. This will be our normal vector, and we will do this, but computers can't do differentiation as we do it on paper, so we'll have to approximate it, and let's implement that. I'll create a function named get normal, which takes in the fragment, and let's define E, which is epsilon here, 0.001, and for X we will use this like gradient in the X direction. We'll approximate it like so. We will use P plus vec3 E. We are basically using the limits definition of a derivative for approximating this. Now for the y direction, so guys, I am using ShaderPlayground. So ShaderPlayground is a WebGL based platform. It's a simple implementation that I have created. You can implement any fragment shader in real time on your web browser. You can access it, but right now I am having some issues with GitHub pages, so it is not live. It is running on my local machine, but soon I'll fix that so that y'all can try your hands on it. Let's do it for Y, then Z. Here we go. Now one thing, this is a normal vector, so we'll obviously have to normalize it, and we will return the normalized vector 3. Let's pass in x, y, and z here, like so. And now what we can do is, using this point, we can get the normal for this. We will use our method. Hello Suraj. Suraj, I am using my own platform, like it's called ShaderPlayground, which is basically a WebGL based implementation where you can, try out fragment shaders written in GLSL. Uh, and it basically lets you run fragment shaders in real time, so on your browser basically. So you can try it out, but right now it's not live because there is some issues with GitHub pages where I hosted it earlier, so I'll be trying to fix it, so you all can also use it later. Let's pass in P, like so. And for the lighting model, I'll be using the basic Phong model. So let's say we have a surface right here. This is the surface normal, and light is incident in this direction, reflected in this direction. Incidence and reflecting angle are equal. So basically we have three components of lighting. There is ambient lighting. I'll denote it with A. So ambient lighting is basically lighting which is uh, always present. There are some global illumination reflections happening, like indirectly light reflects from other sources, or let's say during night time the moon shines and there is a constant small amount of light. So that is the ambient light, what we call. And there is a diffuse lighting. So basically diffuse lighting is uh, it happens when like let's say we have a light incident on this surface and there are particles, atoms basically of this surface, and this light energy, some of the photons are absorbed by this surface. It collides with some of the atoms inside. Some of these photons may lose energy and they get completely used up. Yeah, Suraj, I programmed the shader from scratch. And right now we are doing Raymarching to implement a simple scene and basic lighting models. We'll also be implementing shadows. So I'm just explaining how I'm implementing things while I code it. So some of these particles would get completely dissolved in here, and others, while colliding, they emerge out, and that is known as the diffuse lighting. And the light that is directly reflected, it's specular lighting. So I'll call this as L, this as R. So for calculating the diffuse lighting, we'll just take the dot product with the normal vector and the light direction, incident direction. So let's calculate the vector L, which is nothing but the direction at which the light is shining on the surface. So it will be light position minus P. P is nothing but our fragment. So let's create a vec3 for defining our light position as well. I'll right now keep it at 2 along all axes, and yeah, we have the light direction. Now we Yeah, Suraj, you can do simulations with it using Shader Playground. It is actually, I have implemented this platform using graphics programming, and it basically abstracts away all the nitty gritties and details of graphics programming and provides you with this beautiful interface where you can just type in your fragment shader code and experiment with shaders on your browser. You can even use it on your phone. So let's get the view direction. View direction is basically the direction from which we are trying to view the object. So right now we are along the Z axis and facing the object head on. So I'll use RO minus P. RO is basically our camera lens position. So we'll be viewing from that. Now let's find the reflected vector. There is a method in GLSL known as reflect, which gives you the reflect vector. So I'll directly use that method right here. Now let's calculate the lighting factors. Let's calculate the ambient first. So I'll keep it a constant for of 0.1. For diffuse, uh, diffuse will just take a dot product and we will just use a maximum value. We don't want the product to go negative, otherwise it will mess up our lighting, and basically the internals of our geometry would be lighted. We don't want that, right? Because we are viewing the object from outside, not inside. So we will use the max function here, and we will take the dot product of L and N. L is basically the direction at which light is incident and N is our normal vector. And for flow, for specular lighting is basically the light which you see when an object shines directly. You know that white spot you see when a light is directly shown on an object. So for specular highlight, it is really strong. So we will raise it to some power. So let's, and we will also use the max so that the dot product does not go negative. Let's raise it to a power of 32, and I'll create a variable named form, which is nothing but our lighting model, and I'll just add up these components like so. And let's create a variable which will hold our material color. Let's give it orange for now, and a variable named color I'll create it, which will just multiply our material with the Phong lighting model, and we will just apply this to our fragment color, and see, instantly we have a sphere rendered and the lighting model implemented as well. You can see there is specular highlight. This white spot which you see, it is a specular highlight, and this half of this is less bright. This is diffuse, and the part behind is the ambient lighting. Suraj, it is not the monitor issue actually, it is the aspect ratio scaling issue. So if I have to explain it in short, like Suraj is asking like why in old monitors or old programs uh, a circle visible as a sphere. So what happens is, let's say you provide the coordinate vertices for a circle in clip space. So clip space is nothing but a square which ranges from -1 to 1 like so. And let's say this is your circle inside here, and now what you do is, let's say this is your monitor screen here. It is running on, let's say, 1920 by 1080 resolution. Now what happens is, uh, after rasterization, uh, the fragments inside these circles are colored, like the pixels inside of this circle are colored, and you see the colored circle, and now this square is mapped to your screen like so. So this corner is mapped to that corner of your screen, this to this to that, and this one to this. So basically what is happening, this square is getting stretched in order to fit this rectangular screen. And that's why in some programs you see uh, the circle getting stretched and becoming an ellipse like so. In order to fix that, we multiply the x coordinate of each of these vertices with an aspect ratio. Aspect ratio is basically specific to your screen. So for this screen resolution, aspect ratio would be 1920 divided by 1080. We will multiply this with your x coordinate, and this what it will do is, it will basically transform the space in such a way so that this square, uh, like the space appears to be square, like the space appears to be rectangle, but it will actually be a square, and you will see a circle in proper way. So those programs that you are talking about, they don't have aspect ratio factor taken into account. That's why it looks that way. So guys, I'll be back after a short break, and till then you can listen to the music. I'll be right back. Hello again. So I am back, and till now, what we did is we just used Raymarching to render a sphere and implemented a basic Phong lighting model to add the depth to this render so that we can really understand if it's a sphere. And we just created a skybox, a simple using gradients. And right now, you can see the power of ray marching. Like, I'll explain it to you on this whiteboard. So basically, if you have to draw this such a high quality of sphere, uh, you'll require, hundreds or thousands of vertices to make this proper sphere. And that computing these vertices would be really, compute intensive. But in this case, what we are rendering it on a canvas using just ray marching and a math function, and we just require 6 vertices for this because our canvas is nothing but a quadrilateral or a rectangle, you could say, which is made up of two triangles, each having 3 vertices and 6 vertices. So you can compare this, like, we require 6 vertices to render such a complex thing using ray marching. And like in case of traditional rasterization method, we'll uh, require vertices, and that could take up to hundreds or thousands of vertices depending on the quality of sphere that you are trying to render. So this is where ray marching shines, but it can quickly get nasty because you're trying to pass a ray through each and every pixel, so there are some optimizations that can be done for that as well. But we are not going to get too deep into optimizing right here. We are just making sure that our ray does not go too far and optimizing in that way. So our sphere looks lonely, but before that, let's make the light rotate. So what we can do is we can make our light rotate, and we can use polar coordinates to do that. And I'll make it rotate with time, like so. Now you can see the light is rotating in real time, and everything is calculated in real time. Now our sphere looks lonely, and let's add a partner for a sphere. Let's add a box. So I'll name it as SD box. Vec3 for the coordinates of the fragment, and we will also provide another vec3 which will be the volume, like the dimensions along each axis, like the length, breadth and height. And what we will return is so for a box, let's say we have this box, so let's consider a box which is centered at origin. This is our axis right here, and let's consider half sizes of the box. I'll name it as XX and this as SY. Basically half size along X and half size along Y. And let's say we have our point right here. There will be 3 cases for the SDF right here, like so. So let me draw a line for partitioning like this. So these are the 3 regions where we will calculate SDF. So let's name this 1, 2 and 3. So in the region 1, we can directly find the SDF of this point P right here. we know the distance of this point P from uh, y-axis or the origin. It is nothing but its x coordinate, and we will just subtract the half size along the x of that box. So for region 1 we have d equal to p dot x minus sx, and let's say if p is inside, then it is negative, so it is following our SDF definition. Now coming to our region 2, similarly we can find the distance for that. It's the same condition, just it is flipped, like it is along the y-axis now. So distance in this case will be p dot y minus sy. And now moving on to case 3. For case 3, basically we'll be finding the distance of our point P from the origin, and basically now we'll have to use the distance formula here. Like we'll find the distance from this vertex. This will be the closest to this point in this region. So in this case D will be using the distance formula p dot x minus sx whole square plus p dot y minus sy whole square, like so. Now we have a piecewise function for our SDF, and in order to make it useful we need to combine it into a single function. If we look closely, this one is right here and this one is right here. So basically this is squaring these two and just taking a square root in the third case. So we can, the third case is a generic case, we could say, and we can come up with a simple formula. And right now we are just calculating it in the first quadrant, because due to symmetry it will also be applicable in other quadrants as well. So we will just use the length function here, and we will use absolute value of p minus b, and we will use a maximum function and clamp it to 0. Like so. I think this should work. Let's try it. I'll replace this with SD box. Something's wrong. I think we should take out the, yeah, we should take out the B. Yeah. Right here we have our box. We just took out the B from the absolute, and we have our box right here. We can even move this down a little bit. Like for translating it, we can just, before passing the UV coordinate to our march function, to our map function actually, we can just, let's say, add 0.4. It adds along all the axes, so we need to we will just split open this, and along the y-axis we will add 0.4. Now see, it translates down. Suraj is asking, can we add custom textures? Are you asking on ShaderPlayground? Yes, we can add textures on shader playground. For that, we'll have to use a sampler 2D, which will just sample each and every texel from our provided texture. But right now, I don't have an interface for that on this web application. It For adding a texture, you'll just have to add it into your uh, local local folder, and from that you can just extract it. But I'll soon add that interface here so that you can just drag and drop your texture. I am working my way through that. So now we have our box and our sphere in place. Now what we can do is we can take union of both and render a scene where we will have a floor which is nothing but a box and a sphere on top of it. So let's create a variable named float ds, which will be distance from the sphere, and it will use sd sphere. It will take in p. It has a radius of 1. Let's create float db, which is distance from the box, which will use our function sdbox. And for this, what we will do is we don't require uh, uh, you know a cube. We require a cuboid, and it will be really thin along the y-axis, and it will span, let's say, 50, like so. Yeah, we need to return as well. So for taking a union, we will use the min function. Hmm. Something is not working here. Let's see. Let's use one. Yeah, it's visible now. What I'll do is I'll translate this cuboid below. I'll again use the same method right here. I'll add, let's say, 1. Yeah, it is placed below our sphere, and now I can scale it a bit. Along X, I scaled it as 50. Let's scale it along Z as well, like so. We can see a bit of, you know, artifacts here. You can see like this box is bending around the sphere. We don't want that. This is happening because the limitation of the number of iterations that we have put in our marching function. So let's say if we change it to 200, yeah, now it looks much better. Let's try 500 maybe. Yeah, even better. Now we have this, and what I'll do is, with this in place and our lighting in place, I can add shadows to this. mm, yeah, let's add shadows. So for shadows we'll use Raymarching again, but this time what we will do is let's draw our scene here so that we can visualize what we are trying to do. Let's say we have a sphere right here, and our light source is placed somewhere here. This is L, and this is our object O. And let's say we have a fragment P right here. What we will do is we will project, we will shoot a ray from our fragment itself, which is P, towards the direction of our light, like so. And while doing that, we will march along this ray and try to figure out if this ray is intersecting with any object around. So in this case, it is actually getting really close to the surface of our sphere. So in this case, this fragment is, the light rays are not shining directly on this fragment here. So this would be unlit, and hence it will be in shadow. So we will render it as black. So this will be in shadow. And let's say for this point P here, P dash, light rays are directly falling onto it, and it will fail the Raymarching test where it won't hit any other object in this direction. So basically this will be a lit fragment, and we will just light it using our Phong model. So let's create a method. It will return float. I'll name it shadow. It will take in the fragment position, and we will also pass light position. I'll call it LP. Now we need to find the direction in which the direction of the light with respect to the fragment. So let's name it L. I'll normalize it, and it will be LP minus P. And now what we will do is, we will, just like Raymarching, we'll create a variable named T for accumulating our distance. We will also create a variable named max distance. So this is nothing but the distance of that fragment from the light. So let's say if we exceed that distance, then we don't need to compute any shadows, right? So we will just find the length of LP minus P. We have that, and let's create a variable named res, which is nothing but result, and this will be the thing that will contribute to our shadow. I think that's all we need. Now let's go into a for loop. And for shadows, we are not traveling really far, so I think around 64 iterations should be enough. We can change it if we feel it's not right. What we will do is, we will get position of that fragment. So P plus T times L. L is basically the direction, and let's get the distance here using our map function. We will pass in our position like so. We will also check if D is less than epsilon. So if D is less than epsilon means our uh, ray is certainly hitting an object, and that fragment is being occluded from the light. So it will certainly be in a shadow. So we will just return 0, which will just delete that lighting factor for that fragment. After that, we need to accumulate the penumbra of the shadow. So we will use that, a min function basically, and what we will do is, we will multiply it with a constant k. Let's create a constant k here. Let's keep it 10 for now, with the ratio of D and T, like so. So D is the distance of distance of that point from the surface divided by the total distance we travel to reach that point. And after that we can just accumulate our t like so, and if t is greater than max distance we break, and then we return. We will clamp our resultant between 0 and 1 like so, and we have our shadow function ready. And in this lighting function we will just calculate shadow. I'll name it as sh. I'll call the shadow function, and I'll pass in p, and we need to pass in the light position like so, and I will multiply it with the diffuse factor and the specular factor. I'll leave the ambient as is. Thanks, Sarbik. So right here we are using Raymarching. So like in layman terms, like it is basically we are you know defining some mathematical functions, and using those mathematical functions we are trying to uh, create some amazing scenery and lighting on our screen. It's basically the backends of any games that you have played. This is how they render stuff on your screen, like if you would have played any kind of game. So like there are multiple rendering techniques, like there are graphics apis just something which allows you to draw graphics on your screen using your GPU. So they use something known as a rasterizer. So they use a rasterizer, and basically what a rasterizer. Yes, Arbik. I am building a game engine. It is known as a crochet engine. I named it crochet because making a game is just, it takes patience and lot of skills and lot of viewing to make a game. So hence the name crochet. So I am making a crochet engine, but this is also one platform that I have created known as ShaderPlayground. It is a web application that allows you to run fragment shader and experiment uh, running the fragment shader on your web browser. You can run it on your phone, laptop, anywhere on a web browser, and basically it abstracts away all the heavy graphic stuff behind the scene, so that you don't have to sweat yourself implementing those nitty-gritties and details. So it's just an interface, and I am just demonstrating Raymarching method. Suraj is asking OpenGL versus WebGL, what is the difference? So Suraj, OpenGL basically runs on your system locally, and WebGL allows you to render on your browser. So basically it at the end it uses the GPU on your system, but it allows you to render on the browser. Hi Vishal. So we have the shadow factor multiplied. Let's run this shader, and all of a sudden everything went black. This is because we are facing self shadowing. We in the shadow function we set the starting point of the ray marching as 0 0. We will have to set it a bit higher, otherwise it will self shadow itself. Let's make it 0.02 and it should work like a charm. See, the shadows are working dynamically. Sarbik is saying don't make like Unreal Engine 5. All I know, dev's perspective. UE5 is easy to use for games, but UE5 games are so hard to play right now. System requirements are too much. Yeah, Sarbik. So the goal of my engine is basically to make it super intuitive, not like Unreal Engine or Unity. Obviously, it will take some features inspired from those engines, but the end goal is to make it super intuitive. So let's say if you have minimal or no coding knowledge, even then you will be able to make your own games. And talking about the system requirements, it is not about the engine. It depends upon the kind of textures that you use. So let's say if you use the HDRI textures, so those eat up a lot of memory. So basically, at the end, each of these textures and these vertices are loaded onto your GPU on a buffer, and basically you fetch that data. GPU fetches that data from the local GPU memory. So GPU memory is divided into three. Like there is local, global, and shared memory. So these vertices that of a model or something, they are stored on a local memory or a constant memory that you call it, where you don't have to change the data as much. So once you upload the data from CPU to GPU, it just stays there. And yeah, so the memory has some limit. The video RAM that you call it, it could be 16 GB or whatever it is, depending on the graphics hardware that you have. And these textures and all are loaded onto that VRAM that you have, and that is basically uh, what is processing all that stuff, and it is actually acting like a buffer. And the HDRI textures that most of the Unreal Engine developers use, it takes up a lot of your VRAM and yeah, slows down your performance. Suraj is asking what system are you using? Currently, like I have i5 13th gen and a NVIDIA graphics card RTX 3050. Alive to Play is asking, are you making a a game scene simulator? You could say that, but this is currently not a game scene simulator. Like this is Fragment Shader. Like this is a platform which I have created named ShaderPlayground. So this allows you to run Fragment Shader in real time. So you can use it for not only for games, any kind of scientific simulations, uh, cool UI or particle effects, and even rendering game stuff. Like you can do a lot with shaders. And yeah, I am also making a game engine from scratch in OpenGL and C++. So it will allow you to create games as well. So these are completely two different projects I'm working on. So right now we have implemented shadows. Yeah, Suraj, it works fine for me. Like it depends on the number of rays that you are using for ray tracing and the renderer that you are using for rendering your final output in Blender. So once you understand all these concepts that I'm doing right here, you can easily optimize and customize Blender in order to make best use of your hardware, because underneath the hood a Blender is doing all these things, but it is like hugely abstracted. Okay, so right now we have shadows in place. We have a basic lighting model, and we have SDFs for a sphere and a box and a skybox we have created using a simple gradient. Let's add in a few more things. Right now we have just given a simple color to our flooring and our sphere. What we can do is we can let's add one more sphere before doing that. I'll call it DS1, and let's make it slight bigger, and I'll have to shift it, translate it basically, so that it does not intersect with our previous sphere. I'll translate it along X. Yeah, I'll have to use it here as well. Like so. But right now it is blocking away the other sphere. Let's translate it away. Right now we are seeing some artifacts with the shadows. It has to do with the distance. Let's change this a bit. Rather let's make a cylinder. Yeah, that would be better. And right now we have the same color for both of these, so let's create a structure. I'll call it hit. And it will contain the distance and an ID for what kind of object it has hit. Alive to Play is asking, how can you write entire code without any editor? Uh, I I don't think I understand your question, like what are you trying to understand? So right here we have a editor for the fragment shader, and rest of the things they are basically already implemented the backend in WebGL and JavaScript. Is that your what you're asking? Compiler. So this is like basically when you open this in your browser, it is like there is code, like if you inspect this, I have written it in JavaScript in order to compile the shader. Let me show it to, yeah, you can see this is the JavaScript code that I have written. Basically we have a string basically which is storing the vertex and fragment shader, and this is the fragment shader which we are writing right now. And there are some methods that I have created named create shader and create program. These compile the shader like on this button press, and thus it gets compiled. I hope this answers your question, if that's what you meant. Oh, okay. Uh, Without autocorrect, I think it's more of uh, you know mashing your fingers on keyboard. Like you don't need autocorrect. The more you mash your fingers on the keyboard, the more easier it becomes. That's what I would say. Yeah, so we have a structure named hit. It contains the distance and an ID. So let's say if we have ID equal to 0, then it's a sphere. For ID equal to 1, it will be a box. So we'll have to modify our methods in order to incorporate the structure. So our map function just returns the distance, but we also need to uh, you know return the ID as well. Let's see. So this will return a float, which is our distance, and from the map function we are basically returning the minimum of these two distances. We are basically taking the union. So this should return hit, and even the marching function should return a hit. Sure, buddy. Good luck for your journey. I am not that good. Like, there is a lot of things to learn, but yeah, you can get there with practice. We have this. Hi, Shekhar. Welcome to this channel. So, uh, so I hope you know what we are trying to do here. If not, Basically, I have been working on a project of mine. Like I'm working on like a game engine, a custom game engine made from scratch in OpenGL and C++. And yeah, basically the goal of this engine is to make it super intuitive. Like Unreal Engine and Unity are like great, but they are not specialized. Like they try to provide abstractions for all types of games, and that is really unnecessary, and they don't provide flexibility to customize it. So I'll be the crochet engine that I'm working on, it will have a not so much of a steep learning curve, and it will consider you know guys who are guys who know minimum to no coding, and that will actually allow artists who don't have a coding background to create game or uh, arts using my game engine, and that will truly bring out the creativity within them without the lack of coding knowledge blocking them. Suraj is trying to learn OpenGL and graphics rendering. That's good, Suraj. Good luck for that. So it should return hit. Hmm, I'll create a variable named hit. This should be hit, and it will provide us with, I'll call it as h now, and we will do h.d for accessing the distance. In this case it will be h.d. Yeah, that's all right. And in this case we will return hit t comma the id, basically h.id, and in this case we will return -1 for both when it does not hit any object. I think that's good, and let's change this to hit as well. I'll just remove this line. ID for the sphere is 0 as we discussed. Let's change this to hit as well. Let's say we can do it in other way. We compute these distances, and if let's say ds is less than db, we return hit ds and type 0, else we return hit db and type would be 1. I think this should work. Yeah, and in the receiving end We will also, like, we were earlier receiving a single float, so right now we'll have to convert it to hit as well. It will return, yeah, so we'll use t dot d right here, and let's make changes wherever t is used. For shadow also, I don't think for shadow we require that. And yeah, yeah, now we get an id as well. So let's declare the material like this. Now if t.id equals 0, material will be orange, let's say. Else let's make it a lighter shade of gray. I'll use 0.6 maybe. Let's run this. There is some error. Let's see what's the error. Frag color name. Okay, I think that's earlier error. Let's run it again. Yeah, invalid operation for structs. Yeah, we are actually using the map function again in our get normal method, and we are not incorporating that within here. So basically we'll just use dot d and dot d, so that we just subtract the distances and we don't have anything to do with the id in this case. Again error. Let's see what's this. The same. Cannot convert from structure hit to float. Invalid operation for structs. Okay, let's see. Yeah, we are using t right here. We'll have to do it as t dot d. Somewhere else we are using t, and we'll have to change it accordingly. Let's see where it is. Cannot convert structure hit to float. It's returning hit structure, and I'm trying to assign it to a float basically somewhere in this code, which is creating this error. Let's try to find out where I'm doing that. This is fine. This is fine. This looks fine. Can you all spot the error? Like, where do you see t being used as a float, but we are returning hit value? Let's clear this, run again. Good night, Suraj. It's hard to find really small bugs. Mm, it has to be somewhere around here. Floaty. This is fine. We are comparing h.d. That is fine too. In the shadow function, I don't think we require that because it is just returning a float. We don't require any ID because shadow does not depend on the material of that object. So it has to be somewhere in this main function itself. We get hit defined returned by this march function. Then we compare t.d. Are we using a map function? Yeah, the problem is right here. We are using the map function here. Yeah, so we just use a dot d, and now we have different colors. Finally, finding a simple bug is really difficult. Yeah. So the issue was that we changed our map function to return a structure a variable of type hit, which is a structure which stores the distance as well as the ID. But in our shadow function, which we never suspected would have any error, uh, when we are fetching the distance using the map function, we were basically trying to assign a structure of type a variable of type hit to a variable of type float, which is wrong. So we just have to get the distance and it works. Let's create an SDF for one more shape, and then I think we'll wrap up the stream for today. So I'll create SD torus and take in radius. Radius should be vec2 because Torus is basically two circles uh, and some translation, like if we discuss. So basically we draw this circle like so, and then we make it rotate around this bigger circle in order to get this tube kind of a structure, which is our torus, like so. So for rendering this, we'll have to create an SDF for this. So we can just uh, first generate this circle and then this circle, or other way around. So for SD torus, let's return length p minus r first, and what we will do is, see, this is our y-axis, this is our y, this is z, and this is x. Now our sphere is, you know, being using making use of all these three axes, like x square, y square, z square, and that's our r. Now what we will do is, we will delete our y factor from here, so our circle will only move in the locus will only move in the xz plane, and then it will extend like along y. So we will get a cylinder. So just make it xz using swizzling, and let's just replace that in our map function. I'll just replace it with SD torus. Like so, and this should be t dot x, like so. Now we have a cylinder. We can do really interesting things with it, but let's say, like, first we will try to create this bigger circle, this one. So this is in our xy plane, right? So let's make this xy. Let's make this xy. Yeah, we have that. Now we will store it, let's say, in another vec2. I'll call it as q. And I'll store the y coordinate as the second member of this vec2. And while returning, I'll just use this q. Like so. That doesn't work. Let's try to, change the radius a bit. Like so. We are getting something interesting right here. Something seems to be wrong. Let's see what's the issue. So this is basically a circle in the xy plane. We are storing the y coordinate. We should be storing the z coordinate actually. And now it should work. Yeah. like so. And maybe we should translate it a bit upwards. I'll change its thickness to, let's say, zero point 0.5. And we are seeing some artifacts again, so let's try to fix that. Let's make it 0.02. It's still there. Mm, how about increasing the iterations? No. Let's make it. It works. Let's try to bring it up. Hello Purple. Uh, this is not software actually, this is a web application that I have made. It's called ShaderPlayground. It's made in WebGL and JavaScript, and it allows you to run fragment shaders in real time, and you can, write your own fragment shaders and, make simulations and stuff. So actually this was hosted on GitHub pages earlier, but there is some issue with my GitHub pages which I'll have to fix, and after that you all can use it as well. This is not a software actually, like a web application if I have to be precise, and it is running on the browser directly. Currently I am running it on my local system because the one which I hosted on GitHub pages has some issues. So we have done this. There is some issue with the shadowing part of, and Purple, I think you are new to this channel. So like I have also been working on a custom game engine which is called Crochet Engine, and it is made from scratch in OpenGL and C++. So the goal for that engine is basically making it super intuitive and decreasing the learning curve, like the steepness of the learning curve, so that even a person who has minimal to no coding experience can use that game engine to render any uh, 3D models or create their own games. It is still a work in progress, and there is a lot of things to be implemented in that. But yeah, uh, the existing game engines like Unreal and all are really great, but they have a steep learning curve, and let's say you have to make really good games in that. Like obviously there is an option for blueprints, but you'll have to use C++ at some point. And let's say you are an artist who has a great idea for a game, but you might be lacking proper programming skills, and that may stop your creative juices from flowing. So my engine would come in, and that would basically be super intuitive, and you won't require any coding experience for that. And you can make game like kind of like drag and drop style, and yeah, basically like that, and it will make it simpler for artists and other hobbyists to make their game using my game engine. Guys, if you have not subscribed, please consider subscribing to this channel for more such live streams and videos. I am also working on a tutorial series for graphics programming and uh, rendering, and I'll be uploading those videos soon on my channel. So if you are interested in learning, that would be really helpful for you guys. Okay, so we have implemented SDFs of a few shapes. Let's try to shift this torus a bit upwards. I think a bit more. Yeah. And we can also, make it lay flat if we just change this to XZ and this to Y, like so. You know what? We can also create a pillar, like just for fun, using some math. I'll name it SD pillar, and let's provide a radius for that. Uh, let's create a variable named rad and store radius into that. And what we will do is we will keep uh, subtracting from the radius as we go up. Let's keep it 0.06 times p dot y. Like as the height increases, the radius will decrease. And let's return this. And let's try using SD pillar here. So yeah, we'll have to constrain it along XZ. Yeah, now we can see like the radius is decreasing as we go on top. We can bring our camera back a little so that we can get it into a frame. Let's change it to 5, like so. And what we can do is we can just reduce the size, or maybe it's fine for now. We can play with the radius itself, maybe try building some patterns with it. Let's subtract this. I need something periodic, like this should have some bumps like crests and troughs along its perimeter. So I'll use a sine wave for that, and based on the angle I'll just wrap around that sine wave like along the cylinder. So let's use 0.5. Let's make it 0.01 actually. And let's use the angle. I'll calculate the angle right here. We will use arc tangent. Okay, no difference. Maybe let's try to multiply it with something. Let's say 10. No, we don't have anything yet. Maybe one thing we can do is we'll assign a variable d to that. p.xz. Now, actually, we have an infinitely long cylinder and we need to cut it basically. So, what we can do is, let's say this is our cylinder. We will just cut it with help of a few planes. So, this plane would be nothing but y is equal to y naught, let's say, and y is equal to y1. And this will just clip our cylinders to the certain height that we require. Let's do that. P dot y minus 0.6. Yeah, we need to return d. Yeah, we must take max, right? Because we are not trying to find a union of these two, we are trying to find intersection. So we just clipped it. Let's try. Five is too long. Let's try 4. Yeah, better. And we can do the same for the bottom as well. For the bottom, what we will do is we will just invert the y-axis and do the same like so. Now we have cut our pillar. Like so. Still we don't see any patterns here. Something seems to be wrong. Yeah. Yeah, now we can see slight patterns here. If you can see closely, we will make it much more visible. What if we add this? Yeah, it's much better. Let's make it a bit more prominent, like so. Now we have these patterns. We are getting a few artifacts in the shadows. Maybe we can fix that by changing the K factor that we set to 10 earlier. Let's try 20. Yeah, this is much better. Yeah, this is a lot better. We can also do this wavy thing with our torus as well. It would be interesting. Let's try that. We will require a vec2. I'll make it uh, okay, so we'll use R1 here. Now R1 minus equals, we can use the same formula that we used here. We'll also have to compute the angle first. Yeah. Now see, we have a beautiful floral kind of a pattern with the torus. Like uh, we are just changing the radius of this torus using a sine wave, a transformed sine wave. We can also multiply it with a greater factor. We'll get much sharper. This can create a pumpkin kind of thing if we manage to change the radius. Yeah. See, we already have a 3D model here. We have already created a pumpkin now. We will change the light position so that the lighting is a bit better. Yeah, much better. Let's increase this radius a bit more. Guys, using Raymarching we can also do sculpting. So maybe in our next stream, related to Raymarching, we can try sculpting a model or something using Raymarching. That would be fun. Let's try to create a pumpkin. I'll change the radius here, let's say to 2. It's even larger. I'll have to change the light position as well. I think I'll reduce the radius a bit. Yeah, this looks much better. And maybe let's put the light source at a constant position now. This is better. Maybe I'll increase the ambient factor a bit. Let's pump it up to 0.2. Yeah, looks much better. Or 0.12. Yeah, let's play with it a little bit. Looks better. Now we can add this pillar that we created on top of this pumpkin. So like that green part that protrudes on top of the pumpkin, we can create that with the help of this. So in our map function, let's create a variable named float t. I'll name it as sd pillar. I'll have to create nested conditions in here. If ds is less than d, then return this, else d2, and let's say if db is less than d, then we will return this. Like so. Yeah, we have this on top. It's a bit messed up. We'll try to fix that. Much better. And let's try to reduce its radius. Let's make it 0.1. 0.2 maybe. Yeah. Yeah, this is much better. Now for the height of this, we'll have to clip it. Like so. This looks perfect, I think. And now we have to color it green accordingly. So here let's add an else if condition. 0.5, let's say. Yeah, we have it green. And what else can we try? We can maybe add two eyes to this. Currently this whole code is getting a bit messy, but yeah, we can look into the optimizations later. We have SD sphere right here. We can use the spheres for the eye socket. We'll have to add more conditions here. This will be really painful to add so much conditions. What can we do for this? This code has too much of branching, and I know, but this needs to be instead. What we can do is no, min function won't work on this, right? Or better, we can create a custom min function which returns a hit. Min hit, it will take hit A, hit B, if A dot D is less than B dot D, we return A, else we return B. Now it will be much more simpler. Now let's switch, like delete all of that branching. Let's convert it to DT, and DB is for our ground. Let's add comment so that we are not lost. I think no need because these functions are self-explanatory. And for pillar we have that. Let's add something for sphere, ds1 for the first eye. .1, let's say. It will be ds2 for the second eye. Now we'll have to do it pairwise. For each we'll have to create a hit variable first. hit T for Taurus. It will be 0. Hit box. P for pillar. Will take into S for sphere. And it will take in DS1. Will take in 3. Like so. I will have to compare them pairwise. First, let's check minimum of T and B. Then out of those, minimum of P and S1. Min hit, actually, the custom function that we created. S2 right here. We have some error, let's see. No matching function. Okay. P redefinition. Okay, my bad. Let's name it P1. Yeah, it's working. For the spheres, right, we need to position them, let's say we add 0.8. see those spheres. What's the issue? Yeah, here it is. Let's make it 0.2. And if I, yeah, so let's make it 0.1. Yeah, we have this here. I need it to merge with our pumpkin for the eyes. Let's try to find the exact distance. Yeah, this is much better. Let's make the radius to 0.2 and let's shift it along x 0.4. Let's make it 1.5. 0.5 maybe. Yeah, and on the y we'll shift it by 0.2, maybe 3. Yeah, better. Now we will do the same but in the opposite direction. Like so. Now our pumpkin has 2 eyes. Now for the smile, what shape can we use? What can we use? I'll basically have to use a clipped torus, right? So let's say I have my torus like so. I need to clip it with some kind of a plane. Y is equal to y dash, let's say, and I'll get this one. So basically I'll have to take a difference, and for difference I'll just use maximum of the SDF of A and negative of SDF of B. That should ensure that I get this difference. Let's try to change the lighting a bit as well. I need some soft lighting. What should I do for that? This one looks better, but yeah. I can even change the specular factor. Let's say to 2. Uh, yeah, this is okay. How about 100? Let's try 50. Maybe 32 was fine. Yeah. How about 320? Yeah, 32 is fine. I'll just leave it at 32. And let's get to that smiley thing. For that, we'll have to create a torus. Uh, let's name it T1, DT1. I'll use 0.5 and 0.2. I'll just replicate this torus function and I'll name it torus1, and I'll just change it so that it is in XY plane, like so. I have that, and now what I'll do is I'll have to clip it. dt1 equals min of dt1 and p dot y minus let's say 2, and let's create another hit t1 dt1 and material would be 3, and let's just pair it up with this. Now we'll have to change these parameters a bit. I think we'll have to use max. We need intersection, right? Yeah. And I'll just do minus 2.1. Yeah. It is working fine. Great. Exactly the crooked smile that we need, but we need to clip it much more. Um, let's do it. 2, 3. Doesn't seem to work. Why does it not work? So guys who have just joined right now, what we are trying to do is using Raymarching, we are trying to model a pumpkin, the Halloween pumpkin. Yeah, let's bring it much down. Currently it is smiling, like it looks good, but not exactly what we want. Let's Okay, I'll just take a screenshot of this and save it maybe. This one looks good. One more thing that we can do is the torus one that we have and its radius. What I would like to do is I want it to be smooth, not like so. Yeah. This looks much better. Let's try to increase the frequency. This looks even better. Let's try one more thing. We can add one more light source. Let's see. looks okay to me. Guys, what else should we add? Is the ambient factor too much? What if I remove the specular contribution? Yeah, this one looks good too. Let's clone this method stpillar. I'll name it as dpillar1. We are doing really bad following really bad practices here by, you know, naming the functions not so descriptively, but yeah, I think it's fine. We don't want to decrease the radius. We need YZ, right? So let's use that. Let's keep its radius to 0.2, 0.3 maybe. Yeah, and we need to clip it now. P dot x. Yeah, this this would be a great addition for the nose. I hope it's visible now. Yeah. So we just added a nose for a pumpkin. Let's reduce its radius. Point 0.1, not this one. This. Yeah. And now what we can do is let's try to reduce the clipping. Like so. We can increase the frequency of the sine wave actually. We are using SD pillar 1, right? This looks fine. Yeah, I think this one looks great. Yeah, and the lighting is not too bad, but can be improved. Let's try switching the position a bit. How about 2.5? Let's make it 3.5. It's too strong. Let's multiply our diffuse with a factor of zero point 0.8 maybe. Much better. How about 4.5? I think this lighting looks much better than that. And let's remove this factor. Bump up this. Yeah, looks better. How about specular? Specular doesn't look much good on this one, does it? let's add the nose with that smile as well. SD torus 1. We need to rotate it a bit. Let's see how. SD torus 1. I think it's, yeah, with this one. Shift it a bit down. And now we will clip it. Yeah. I'll just shift it above. Yeah, this looks better, lot cleaner. And let's try without specular. Yeah, so we are done. Guys, we have implemented a pumpkin like with different facial expressions using Raymarching on the platform that I created, which is known as ShaderPlayground, which is basically a WebGL implementation which allows you to run fragment shader in real time on your browser. So maybe you can run it on your phone, on your laptop, or anywhere. And actually, it was hosted on GitHub pages earlier, but due to some reasons, it is not hosted anymore. There is some issue with the GitHub pages, and I'll soon be fixing that. After that, you can also use Shader Playground and try out your own Ray marching implementations. So, guys, this was it for today's video. Thanks for watching. Bye. See you all in the next one.